So I hope that you can listen to my voice. Can anyone at least reply in the chat? Can you listen to me? All right. So thank you for the response. Okay. So let me try to adjust something. Microphone. How about now? Is it okay now? Okay. Um. How about now? Testing, testing. Yeah, a bit muffled. Maybe I stop using.
Okay, rather than using this mic, I'm using the PC mic. I think that should be okay. And I will speak up a little bit for the class to avoid any, mishearing. So we come back to this part. Let me. This part of our lecture about ohmmeter, and I have explained about how the basic construction of a series. This is what we call as a series ohmmeter. Basically a series ohmmeter. So today we're going to look at a series ohmmeter and then multi-range ohmmeter and parallel, I would say, series connection. Ohmmeter, and then some explanation about wattmeter based on dynamometer, and if possible, we jump into chapter 3. chapter 3 if possible. But I think we will not have some a lot of time to cover chapter 3 even from the beginning. Right. So coming back to series connection ohmmeter. So the series connection ohmmeter consists of power supply, power supply, uh, PMMC, zeroing resistor or potentiometer, and the terminal A and B where we connect the unknown value, unknown resistor. No, we don't know the resistor that we want to connect in between terminal A and B, and all of these are connected in series. So we know that on the PMMC, so basically the deflection is caused by the input current and the interaction between the input current and the permanent magnet. So when at default, okay, there is no deflection, so I am or the current that flow through the PMMC is equivalent to 0, and then we have our basically here IFSD. Or full scale deflection current. And last week I explained, so when terminal A and B is open, basically the terminal between A and B is open. So in this case, IM is 0 ampere, and when terminal A and B is open, so we can say between terminal A and B the resistance is infinity ohm. Okay, so very high. So no means that the equivalent resistance between terminal and B is very high. So that's why when there is no deflection or there is no current flowing through the circuit, especially current flowing, no current flowing through the permanent magnet moving coil. So at 0 ampere or the zero deflection, here is proportional or equivalent to infinity ohm. But when the terminal AB is closed, or short circuit, there's a proper short circuit. So when a short circuit is an equivalent resistance of 0 ohm, means there is no, when short circuit, the resistance between A and B or Rx is equivalent to 0 ohm, means that there is no deflection. So there is no resistance between point A and B. But when it is short circuit, so the current that flow through the galvanometer is equivalent to the IFSD or the full scale current. So if we find the equation of IFSD, so IFSD equivalent to V over Rm plus Ro. So in this case, we will adjust the RO value until we get the IFSD or the full scale current. So in this case, when the full or short circuit, so we will have full deflection. Full deflection of the pointer, and at this point, okay, the resistance is equivalent between A and B is equivalent to 0 ohm, and IFSD is equivalent to V over Rm. So this is our useful equation number one. So let's say if we measure or we place unknown value of between terminal and A and B. Let's say okay, we put it as Rx so we place Rx, so an unknown value of Rx. So we can write down the current that flow as I, which is I. The I is in between is between 0 ampere to IFSD. So I will deflect above 0.0 ampere and just below IFSD. So that's the current. Then if we calculate or we find the current equation that flow, so we get I equivalent to V over Rm plus Ro plus Rx. So this is our useful equation, and we divide 2 and 1. 2 divide with 1. So this is we can call as the ratio P, the ratio of current to the full scale deflection current, ratio P, okay, which is equivalent to Rm plus sorry sorry yeah, we divide, so we get Rm over Ro over let me show you the step. So here we have 1 over Rm plus Ro plus Rx divided by 1 over Rm plus Ro. And if we rearrange this, we get Rm plus Ro over Rm plus Ro plus Rx. Okay, so now we have our equation, which is the ratio of current during measurement of unknown resistor divided by the full scale deflection current. So let's see how this equation is useful. Here we have our example. 1 milliamp full scale deflection current movement is used to be used an ohmmeter circuit. The meter movement has an internal resistance of 100 ohm and 3 volt will be used in the circuit. Mark of the meter phase dial for reading resistance. So assuming that this is a for series connection ohmmeter, so we can use a table. Ratio P and then the equivalent value of resistance between point A and B, and then I, or current that flow through the circuit. And maybe useful we put a 1 IFSD here. So we can start from one or which is I over P is I over IFSD. So if I is equivalent to IFSD, if if I equivalent to IFSD, so that means it's equivalent to 1. Now, okay, we can put here 1. Then maybe we can put here 0.75, 0.5, 0.25, and 0. So the equivalent deflection percent, this is equivalent 100%, 75%, 50%, 25%, or 0% of deflection. Or if we because the question here want us to mark the meter phase dial for reading, so we can think have a space here. So this is IFSD, or we can say that is 100% deflection. Here is 0.75% of the IFSD, or we can say 75% deflection. And here is 50% deflection. Here is 25% deflection, and this is 0% deflection. So we need to IFSD, of course. Let me erase, try to erase. Okay. Like this. So our full scale deflection is given here as 1 milliamp here. 1 milliamp. That is the full scale deflection here, which is 1 milliamp. So the circuit will look basically like this. So RM used to be a ohmeter. The meter have an internal resistance of 100 RM, and then this our RO. And this is between A and B. This is R X. RX. And IFSD is 1 milliamp. 1 milliamp, and the meter movement has an internal resistance of 100. So this is 100 is RM plus RO. So the battery is 3 volts. Okay. We can use this equation. Okay, the ratio P equivalent 1 over IFSD equal to RM plus RO divided by 1 plus RO plus RM. I have shown you how it was derived here. So we're going to take that equation P equivalent to RM plus RO over Rm plus Ro plus Rx. Okay, we have here they have shown you this ratio on the left. So what is Rx when 100%? The deflection. What is Rx? So basically, if P equivalent to 1, so 1 equivalent to Rm plus Ro is 100 over 100 plus Rx. And 100 plus Rx equivalent to 100 over 1. So Rx, is it 100? Is it 100 minus 100? So that means is 0 ohm, right? If P is equivalent to 1. So we know that when full scale deflection, that means A and B is equal as if it is short circuit. So this is will be Rx will be 0 ohm. So I here since okay, we using this equation, so I pretty much don't need to measure because we only if you want to accommodate the question, unless it is asked to find I just leave it there, so you can feel that your own using the equation, which is P is di over IFSD. So even if P is equivalent to 1, so if P is equivalent to 1, so means that I equivalent to IFSD. So this will be 1 milliamp. So for the sake of exercise, okay, we put the value of I. So it means that when ratio is equivalent to 1, Rx here is 0. And the current that flow is equivalent to the IFSD. So that meets our, so far, our concept. Let's move on. If so if P is equivalent to 0.5, 0.75. So if IFSD equivalent to 0.75, so I equivalent to 0.75 times 1 milliamp, which is equal to 0.5 milliamp. So I is 0.75 milliamp. But what is X, Rx? So we come back to this equation. So 0.75 equivalent to Rm plus Ro over Rm plus Ro plus Rx. And Rm plus Ro is fixed to 100 ohm. That will be 0.75, 100 over 100 plus Rx. So 100 plus Rx will be 100 over 0.75. So Rx will be 133.33 minus 100. That will be 33.33 ohm. So here will be 33.33. So put the unit here, ohm. All right. So we have okay, look at 0.75 ratio. Now now if P is 0.5, so if 0.5 so 200 minus 100 we get 100 ohm. So here 100 and here is 33.3. This is 100. Okay. 0.25 0.25 Here will be 400. So we get 300 ohms. So here is 300. So here we have 300 ohm. I forgot to calculate what is I when P is 25. So P is I over IFSD equivalent if 2.025 or 50%. So I is equivalent to 0.25 milliamps. Here is 0.25 milliamp, and this is 0.5 milliamp. Right. Okay. Lastly, if P is so P. So if P is 0, so if P is 0, so we have here 0 equivalent to 100 over 100 plus Rx. And if we divide 100 to any value of 0, we have infinity and Rx minus 100. So that is infinity. So here is infinity or very large, and I here is equivalent to 0 when P is 0. So if I or Z is 0, so I is equivalent to 0. If P is 0, so I is equivalent to 0. 0. Right. So far, if you look at the scale here, so we have divided the scale into 4 equal portions of deflection, in terms of deflection. But if you look at the resistance, scale, okay, so at 75% we have 33.3 ohm, and then at 50% we have 100 ohm, and at 25% is 300 ohm, and then 0% is infinity. So as you can see that the scale of the resistance or the division of the resistance is not linear. So if linear, let's say linear, if this is 33%, if this 33.3, this could be double like 66, and then this is triple like 99 ohm before infinity. So you can see that the issue here for series resistance, that the scale of resistance reading is not linear with the deflection, or you can say it's not linear to the current, okay, that flow through the circuit when we place unknown value of Rx between A and B. So that's the issue, or some thing that we can understand from the resistance. We Usually for the multi-range ohmmeter, we do not use it to in designing. So usually the value is set uh, in the beginning. And for ohmmeter, then this one is the ohmmeter uh, called as the parallel connection ohmmeter. Parallel connection ohmmeter. So this, instead of having series connection, our zeroing uh, basically our zeroing resistor is connected in parallel with the PMMC, as you can see. So as as you can see, this is an ohmmeter with a power supply of 1.5 volts. We have here our PMMC with 50 ohm internal resistance, and and here our zeroing resistor is 50 ohm at full scale deflection, or 50 microampere. So the question is calculate the scale reading of the meter at 0.5. Okay, and then there's new question, new resistance of R2. Okay, it should be if uh, when EB experience fall to 1.3 volts. And so 0 ampere, and then full scale deflection IFSD 50 micro ampere. So that is when IFSD is full scale deflection. This is when R between the R and AB, between R and B, or RS in this example or question is equivalent to 0 ohm. So the question is, what is the value here? What is RS here when IFSD divided by 2? What is RS according to this circuit? So we can draw the circuit. 50 ohm, and R1 is equivalent to 50. R1 is this resistor. This R1 is 15 kilo ohm, and this is the RS, 1.5 volts. So if half scale, what is the value of RS here? What is the value of RS? So we can use some analysis. And let's say this is IB, and this is I2, and this is IM. And IB is equivalent to I2 plus IM. So that's the first equation. And IM here is equivalent to IFSD divided by 2. So if we apply KVL here, so we get that negative I2 multiply with R2 plus I M multiply with RM equivalent to 0. Therefore, I2 is equivalent to IM RM divided by R2. And IM is IFSD divided by 2. IFSD divided by 2. And RM is 50. And R2 is 50. So I2 is equivalent to IFSD divided by 2, which is 50 ohm of 50, which is 50 microampere divided by 2, 25 microampere. And from this equation from 1, IB is equivalent to I2 plus IM, which is equivalent to 25 microampere. I2 plus IM is also 25 microampere, which is 50 microampere IB. So we get IB is 50 microampere. Then the next step, okay, we can apply KVL. We can apply KVL either here, or we can apply here KVL. Okay, let's do this. Okay, apply KVL here. So we had negative 1.5 plus IB multiply with RS plus IB multiply with R1 plus I2 multiply with R2 equivalent to 0. So IB RS will be equivalent to 1.5 minus IB R1 minus I2 R2. Okay. So if you calculate RS will be 1.5 minus IB. IB is 50 micro. R1 is 15 kilo minus I2. I2 is 25. 50 divide by IB is 50 micro. So if we calculate RS, it will be 1.5 minus 75 minus 1.25 milli divided by 50 micro. This is small. This is very small, you can ignore. But let's put it into the calculation. Right. 0.05 minus 1.25 50 divided by 50 exponent -6. So it's around 14 1475 ohm or close to 15 kilo ohm. Okay, so RS in this design is 15 kilo ohm. So that's how this parallel ohmmeter is designed, and I believe you can calculate the value of R2 if the EB is dropped to 1.3 volts, and then you can find the solution there. Okay, what is the value of R2? Just to before we stop, we just wrap up ohmmeter. So what is the safety and precaution? The precaution is that similar to what we observe for ammeter, always de-energize or discharge, okay, the ohmmeter by short circuit, and then switch off the circuit while measuring the resistance. Why? Because to avoid uh, power loss, of the battery. Yeah, remember that when ohmmeter, in any design of ohmmeter, we require a power supply. Okay, a power supply. So if we let the system setting to ohmmeter without turning it off, so that means that the power will dissipate due to the internal resistance. The power will dissipate by itself. Okay, and also always zero the measurement, okay, by short circuit, or mean touching the positive and negative probe. So that means that Rx is equivalent to 0 ohm, and then we adjust the uh, zeroing resistor so that the reading is at 0 ohm. Right. So the next I think next we will cover on dynamometer, uh, and then I just want to highlight that there are exercises, okay, in this slides that you can refer. Then you can to find the try to solve it, and then all the answer is given. Really, except for that, I think there's few answer, and then if you cannot find the answer, um, you can ask. Except for this question number 18 and 20 is not for this chapter actually. So I think Thursday will be holiday, no class. So the next class we will meet at on Tuesday. Tuesday, and I believe it's still online, because online class is until 14. Oh, only until 14 or 19. When is online class is until when? Anyone know? Anyone? So we 19. So which means, okay, for next week, okay, we will still meeting online for 16 and 18. Okay, so with that, thank you very much. We stop, and then no class for Thursday. So I think I want to say happy holiday. Okay, Selamat Hari Raya in advance to everyone. Okay, please take care and see you back uh, our class online safely next week. Okay, with that, thank you very much.
Shota.
Thank you, Rati. Okay, so we have 2 more weeks before our test. So we have arrived to this part of the lecture about the Ohmeter safety and precautions. So today we will discuss a bit on watt meter. Actually, the idea of a watt meter is to measure the power that is used in a circuit. So it is one of the important measurement in the industry or in the domestic application. So basically, how do we measure power? We, similarly as how we can measure uh, resistance using the combination of ammeter and ohmmeter, and then we can use the for resistance measurement we can use the Ohm's law. As for power measurement, okay, we can use the equation of power equivalent to voltage multiplied by current. So voltage across the load and then the current that flow through the load. So here at the bottom, you can see how the ammeter and voltmeter can be arranged to measure watt or power across a load R. So I will not go through this example, but basically I want to straight go to the principle of watt meter. So we have a look at the concept of galvanometer. So hang on, let me adjust my pen. So we have to look at the concept of PMMC or galvanometer. So it is basically the interaction between a permanent magnet with the current, the measurement current that flow through a set of windings. So that is basically the basic of PMMC or galvanometer. But for the principle of a wattmeter, so it's actually the coupling of between the current, the measurement current, that flow through fixed two set of fixed coil. This is fixed coil 1 and second fixed coil, and then at the center we have a moving coil, and so it's actually the fixed current is generating a set of electromagnet on both sides. So there are electromagnet on this side and also electromagnetic field on this side. So that main current also split into the moving coil to the ground, and then the moving coil will also generate its own magnetic fields. So this also generates its own magnetic fields. So basically, for wattmeter is actually the coupling between the magnetic field that generated by the moving coil with the fixed coil on both sides. So we can say that for wattmeter there is no permanent magnet. There is no permanent magnet, and then coupling between the magnetic fields from the fixed coils on both sides with the magnetic field of the moving coil. So the keyword is that coupling, the coupling, and then the main current that produce the magnetic field is from the main current, or the current that is producing the magnetic field, or the magnetic field is the main current basically. So this is what it looks like for the ohmmeter, the connection. Here you can see this is B, A, this is C. So B is from the main current, and then split here to the shunt current, and then this is the current that flow through the load. So usually the shunt current is small, so that I is close to I prime. I do want to go here in details for the so what I'm trying to say is that the wattmeter can be used instead of the DC, and also work or also work in the measurement of AC. So the power we focus on here in AC circuit. Okay, in measurement the power, the power is equivalent to the V multiply with I. V and I are the RMS. Okay, V is the RMS voltage, and I is the RMS current, and the cos theta is what is called as the power factor. Okay, let's try to find an example. Before we go to that example, so the principle of the watt meter, or the basic device that we have discussed before, it is called as the dynamometer. So basically, a dynamometer, it consists of as you can see, two sets of fixed winding, and then at the center there is a moving coil. So basically, so the connection looks like this. So this is the fixed winding one, and then this fixed winding two. So this is fixed winding one. So and then this is fixed winding two, and then the AC source come from here. And then at the center here we have the moving coil. Okay, moving coil. So as I explained before, the movement of this dynamometer type instrument that is used can be used for wattmeter is basically the coupling between the magnetic field that is produced by both fixed windings with the moving coil. So the magnetic field will the fixed windings will cause the moving coil to rotate, and then the rotation magnitude is proportional to the magnitude of the current. So it can be further modified. Okay, this is the basic connection of dynamometer. If you use this directly to measure uh, the current, it will uh, cause the moving coil winding to break, because we cannot cope with high current. So there is some modification required for the system. So as you can see here, so this is the modification of the dynamometer. Still, we have that here is the fixed winding on both sides, and then in the middle there is the rotation or the moving coil. But the current, as you can see, is split or limited. Okay, the current that flow to the winding is limited by this RV, okay, or shunt resistor here, RV shunt resistor. So you can see here at the bottom here, that's the schematic. So this is the modification of the dynamometer, or the connection of the dynamometer to be used as a watt meter. So let's see some example. Okay, so basically a wattmeter that uses the electrodynamometer movement with Km, 8 degree per watt. So Km is is basically a constant. I will show you the equation. It's used to measure the power dissipated in the AC circuit. If the applied voltage of 100 VRMS produces a current of 0.5 ampere with a power factor of 0.8, so how many degree does the meter pointer deflect? So the equation of the angular deflection theta m is equivalent to Km, which is the constant here, multiply with E, the voltage E, and I, current, and cos theta, which is the theta is the power of the equivalent the equivalent power factor cos theta. Therefore, the angle or deflection is 8 degree watt multiply with 100 volt. I mean, this is the unit. Multiply with current 0. Is it 0.5 and multiply with 0.8. So that's supposed to be I think the current is not 0. Current here is 0.05. 0.05. Therefore, the angle is 35.2 degree. So the angle, okay, what we see here, the angle here, theta, the angle of deflection is 35.2 degree. So that's one example. Value of parameters. So this bridge is called as the Wheatstone Bridge, and then it is used to measure an unknown electrical resistance by balancing two legs of a bridge circuit. As you can see here, it has 4 resistors connected in the form of a bridge, where between A and D we supply with voltage, and then power supply, and between B and C we connect a PMMC or galvanometer. So the process of balancing the bridge can be achieved by adjusting a variable resistor here. So by adjusting the variable resistor here until we get zero deflection, or what we call as the condition when VB minus VC equivalent to zero. So again, how balance condition is achieved? So balance condition is achieved by adjusting the RFR, or the variable resistor here, until it fulfill this condition, which is null condition or null detection, or in other words, that is zero deflection. By the galvanometer or PMMC. So this is the PMMC or the galvanometer. So what is null detection is when there's zero deflection. We adjust this resistor between B and A, the variable resistor value, we adjust until we get zero deflection, okay, or zero detection, or 0 volt, or no, or other words, IG is equivalent to 0, or IG is equivalent to 0 ampere. So in this condition, when IG is equivalent to 0, the voltage between B and C, VBC, is equivalent to 0, or VB minus VC equivalent to 0 volt. So means there is no potential or zero potential in between point B and C. So this is called as the balance condition. So it is achieved again by adjusting the variable resistor. So the variable resistor, sometimes it can be on the other part of the leg, or the other leg of the bridge. It can be here or it can be here. So the point is that we adjust the variable resistor, and then the other resistor are fixed resistor. R2, R3, and R1 are fixed resistors, and one of it may be the unknown value. Right. So here, the other example of Wheatstone Bridge. So R1, R2 can be fixed resistor. So we can say that R1 and R2 are fixed resistor. So initially there is a galvanometer here, G galvanometer, and R3 can be a variable. Can be a variable resistor, and Rx is unknown. Rx unknown value. We don't know the value, so that's why we want to try to find, or to to get the value of Rx. So how we can prove this equation? So we have a galvanometer here. So when balance condition, VA minus VB is equivalent to 0 volt, means there is no deflection, or potential is the between point A and B is equivalent to 0. Or we can say that IG the current that flow here is equivalent to 0 ampere. So that means point A and B is like an open circuit. Okay, like an open circuit. That means there is no current. So when balance condition, we can represent the circuit like this. One, 3, R2 and Rx. So it looks like R1 and R3 are in series, and also R2 and Rx are in series in another part of the circuit, or another branch of the circuit. But both R1, R3 and R2 Rx are in parallel with the power supply E. So we can find the voltage VA and VB separately by using the voltage divider. So VA, using the voltage divider, VA is equivalent to E multiply with R3 over R1 plus R3, where VB is equivalent to E, the potential of VB is equivalent to main power supply multiply with Rx over R2 plus Rx. But we know from here, we know that VA minus VB is equivalent to 0. Okay, therefore, E R3 over R1 plus R3 minus E
multiply Rx over R2 plus Rx equivalent to 0. So if we can work it out on the left hand side here. So E multiply with R3 over R1 plus R3 equivalent to E multiply with this is Rx. Rx over R2 plus Rx. So that's cancelled. So that we have R3 multiply R2 plus Rx. Rx R1 plus R3. So R3 R2 plus R3 Rx equal to Rx R1 plus Rx R3. So this one cancel. And finally we have Rx R1 equivalent to R3 R2, or we can say Rx divide by R2 equivalent to R3 divided by R1. So this is how we can find the relationship, okay, when the circuit is in balance condition. So we can get this relationship. Okay. So let's find this equation. So the figure below consists of the following parameters. R1 is 20K, R2 is 10K, R3 is 50K. Find the unknown value of Rx. So we can assume that this is in balance condition. Okay, balance condition. So you can always derive the equation, or if you're confident, but you must be confident with the arrangement of the Wheatstone Bridge. So this is the node, okay, point where it is connected to the power supply. So if you see this orientation of the Wheatstone Bridge, so you can immediately use the equation Rx divided by R2 in balance condition. The ratio of Rx over R2 is equivalent to R3 over R1, or Rx equivalent to R3 over R1 multiplied with R2. So R3 is 50K divided by R1, 20K multiplied with R2, 10K. Therefore, we get 7.5 kilo ohms. So Rx is equivalent to 7.5 kilo.
Okay.
So we take a 5-minute rest. So 5-minute break. So those who haven't signed the attendance can do it now. So one of the application of strain gauge is is a conditioning circuit for strain gauge. So the strain gauge sensor, basically the strain that act on the relay of the bridge, whose resistance is the resistance change to the amount of force applied to the strain gauge sensor. So a Wheatstone bridge can be used to convert the amount of force detected by the strain gauge into voltage, and then shown by the galvanometer or meter at the between point M and N. So that is one application that is used. So so this is the question. The circuit looks like this. So at night, there is no car on the bridge, therefore no reading shown on the meter. Calculate the value of the strain gauge, or calculate the value of value, the resistance value, basically resistance of the strain gauge if RA equivalent to 250 and RB equivalent to 500 ohm. So let's see. RA and RC is 250 ohm, 250 ohm, and RB is 500. And what is the value of the strain gauge? So let me put that as R as the strain gauge. So we know that the ratio, okay, R as G divided by RC equivalent to RA divided by RB in balanced condition. So means that in balanced condition, where there is no V. So this is when VMN equivalent to 0 volt, or you can put IG, OIA, put IG, OIG equivalent to 0 ampere, no deflection. This is only true when this is condition, or these two conditions are met. Therefore, we can find what estimate what is RSG. So RSG is equivalent to RA divided by RB multiply with RC. So our RA 50 divided by RB multiply with 250. So that's how we get 125 ohm. So that is the answer for this part. So for this part, RSG equivalent to 135 ohm. Okay, and then there's a condition here. During the day, there are cars on the bridge which causes deformation of the pillar. The value of the strain gauge reduced by 0.5 ohm from the original value. What is the voltage reading of the meter? Okay, but this question 2 only applicable if RG, or the internal resistance of the meter, or the galvanometer, is infinity ohm or high, which means that at any condition the current IG will remain at 0 ampere. So if this is not the case, we have to consider the internal resistance of the galvanometer, and then we have to find the voltage reading using what is called as the Thevenin circuit. So it's okay, we look into that. Okay, we assume that number 2. Okay, we assume that the internal resistance of the galvanometer is high, so the IG will always remain 0. Okay, always 0 ampere at any condition. So the thing is that let's redraw. So when RG has reduced by 0.5. So we have our meter here, and then we know that the RSG is equivalent to 125 minus 0.5. So 134. So that's the new value of the RSG, and then the other, like RA remains remain at 250. RB remain at 500 ohm, and RC remain at 250 ohm. And then V in here is 6 volt. So in practical, when RSG has reduced by 0.5 ohm, which means, okay, practically this bridge is not balanced. Or you can say that RSG divided by RC is not equivalent to RA divided by RB. So when not balanced, in practically, IG here is not equivalent to 0 ampere. Or the current, there will be some deflection, there will be current that flows in between M and N. But this question, I assume that IG when this just reduced to 0.5, so it assumed that IG is 0 ampere, but the potential is can be measured by between M and N. So the such device that can fulfill that is like digital voltmeter. Digital voltmeter has RG. Okay, digital voltmeter has RG equivalent to infinity. So it means that it takes virtually 0 ampere current, but it can detect the voltage between point M and N. Okay, point M and N. But let's assume that when this is reduced by 125 ohm, okay, assume that this is in between is in between this in between this port IG is remains 0, so that means that when this is IG equal to 0, it looks like an open circuit. So assuming that, okay, no current, okay, or is can flow through the galvanometer, but still we can see the value, okay, using a digital multimeter. So assuming that, so we can use MN six volt, 250 ohm, 500. This has become to 124.5, and this has become 250 ohm. Therefore, according to the assumption, VM is 6 multiplied with 500. Okay, VM is here, plus minus, and VN is here, plus minus. We use the voltage divider. So VM is 6 multiplied with the DC power multiplied with 500 divided by the total, total series value 150 plus 500. VM equivalent to 4 volt, whereas for VN is equivalent to 6 multiplied 250 divided by 250 plus 124.5. So that is 6. Four point 005 volt. Therefore, VMN equivalent to VM minus VN, 4 minus 4.005 volt, equivalent to 5 negative 5 millivolt. So that's so that is the voltage reading. Okay, for that assumption, right? So in reality, in balanced condition, any imbalanced condition, we need to consider the internal resistance. Consider the internal resistance of the voltmeter or the indicator in between point D and B, and then we have to use the Thevenin circuit analysis to find the value. We cannot simply, in balanced condition, we need to consider right. So let's come back to this this question. But this time we consider the internal resistance of the galvanometer or the voltmeter. Let's say we say for number 2, let's crop the but this time we consider the internal uh, resistance of the galvanometer. We say that let's say Rg or the internal resistance equivalent to 50 ohm. So our circuit will look like this. So this is not balanced condition. And then the idea is what is the voltage reading of the meter, which is basically what is the voltage between point M and N. M N. So what is the voltage? V M N. So to find to solve this, we need to use Thevenin analysis. Then we have to at the end of the analysis, we have to convert this circuit into V Thevenin, R Thevenin, and then this is our node Mn. And this is our galvanometer resistance, basically a galvanometer resistance, which is Rg. So we need to convert this circuit into this Thevenin circuit. Then after that, okay, then we can estimate what is VL. So basically VMN is going to be equivalent to VTH multiplied with Rg over Rg plus RTH. But prior to solve, okay, to get this solution, we need to estimate the equivalent Thevenin resistance seen from between M and N node, and also what is the Thevenin, okay, Thevenin voltage seen from point M and N. Okay. Okay, let's start with finding the RTH. First, we need to find the equivalent RTH. So the first step is to find RTH seen from node M N. So which means that we keep that, we keep the so we want to find what is RTH here. RTH. So we remove the galvanometer, and then short circuit power supply or power source, 6 volt, like this. Short circuit. Okay, so we can let's say rename this point as point A and B. Point A and B node. Point A and B node. And let's retain the value or the name. RA, RB, RC, RG. This is RA. This is RB. This is RG. And this is RC. And then we want to find the equivalent RTH seen from here, from node M and C. So we need to reorganize carefully. So our Thevenin this is not M. This is at the bottom down or the bottom is node N. So node M. Node M is connected to RA and RB. So this is RA. So this is RB. Whereas node N is connected to RC and RG. Yeah, so the equivalent Thevenin circuit or Thevenin resistance seen from point M and N, it looks like this. So you can see that this point A and B is short circuit. So that should short circuit this part and this part. So the equivalent RTH will be RTH equivalent will be RA series the product of RA parallel with RB sum with the product of RG parallel with RC. Okay, so far okay. If you have any question, you can ask. So therefore, the Thevenin value RA is 250 here multiplied with RB is 500 divided by 250 plus 500 plus 124 multiplied with 250 divide 134.5 plus 250. So plus 49.83. This yeah, that's what I got. 59.8. So RTH is 216.490. So let's keep here. RTH is 216.49. VTH is okay. We need to find. Okay. Now we have find the RTH. Next, we need to find the VTH. Okay, VTH. So find VTH in between node M N. Okay, but reconnect basically reconnect the main power source, the DC power source, 6 volt. So reconnect 6 volt. So this is looks like voltage divider circuit. Two parallel voltage divider circuits. So it looks like this. I think we have done this before. 250 ohm and plus minus VM. 150, and then this is 500 ohm, and this is 6 volt. This is our RG plus minus VN, 124.5 ohm, and then that is 250 ohm. So VTH is equivalent to VMN, or equivalent to VM minus VN. So equivalent to 6 multiplied with 500 divided by 250 plus 500 minus 6 multiplied with 250 divided by 125.0 plus 250. I think we have solved it here. So you basically will get negative 5 millivolt in 5 millivolts. So our VTH is negative 5 millivolt. Therefore, finally, oops. So what is the VMN? What is the voltage meter reading? So VMN, so it is our RG plus minus VMN and 50 ohm, 50 ohm. Therefore, actual VMN, considering the internal resistance of our galvanometer, will be equivalent to VTH multiplied with RG over RG plus RTH. And then our VTH is negative 5 millivolt multiplied by 50 divided by 50 plus 216.49, which is equivalent to So it's around negative 3.76 millivolts. So that is the actual answer. Okay, final answer. When there is not balance, and considering the internal resistance of the galvanometer, so we cannot simply use the voltage divider circuit. But for imbalance, okay, or unbalanced bridge, we need to use the Thevenin circuit. So therefore, you can find the Ig. So the Ig will be equivalent, or the current that flow through the circuit is equivalent to VTH divided by RTH plus Rg. So that's the current that flow. Okay, so we have done this exercise on the problem. Then our next topic is Kelvin bridge, but we will continue that this Thursday. Okay, this Thursday. So having said that, I conclude our class for today, and then see you again online next week. Okay, thank you very much. Okay, now we continue. So basically, we know that if the bridge is in balance, we can write as Z1 over Z2 equivalent to Z3 divide all to Z4, or you can write Z2 over Z1 equivalent to Z4 over Z3, so that will give the same meaning. So if this is in balance, find Z4. So directly from the balance equation, we know that Z4 is equivalent to Z2 over Z1 multiply with Z3. So therefore, if we have Z2 150 0 angle divided by Z1 200 angle 30 multiply with Z3 250 negative 40. So the equivalent is that, okay, we 150 multiply with 250, the magnitude part, divide by 200, whereas the angle, so we have 0 degree plus minus 40 degree, and then minus 30 degree. Therefore, Divide by 200. So we get 187.5 ohm negative 70 degree. So that's in the polar form. Okay, next we have this bridge, AC bridge. You can see that there are 4 arms. The first arm here have a pure resistance 400, and the second arm here have resistor in series with the inductor that the value of 1.92 milliohm, and the third have a resistor in series with the capacitor, but in this case we don't know the value of Zx. So to find the Zx, okay, assuming that the bridge is in balance, we need to estimate the reactance value for every arm or for every impedance set. Like R1 is a pure resistor, but R2 have a inductor. So inductor, so we have to estimate the reactance. And also here we on the third arm we have a capacitor in series with a resistor, so we need to estimate the reactance of the capacitor C3. So we can first basically, hang on. So the equation comes first. But anyway, so Z R1 is a pure capacitance, or if we write in impedance, Z1 is equivalent to 400 ohm. Or you can write 400 0 degree. 400 ohm 0 degree. So Z2 is 200 plus J XL, or equivalent to 200 plus J omega L, or 200 plus J 2 pi FL. So that is 200 plus J 2 pi F frequency is 1000, and then the inductance value is 15.92 milli. So that you get 100 ohm. 200 plus J 100 ohm. So if you convert this into polar form, uh, so the real 100, 200, 100. This is basically 200, 224, 26.57. Oh, Z3 is equivalent to 300 plus 1 over J XC, or you can rewrite 300 minus J 1 over 2 pi FC. So 300 minus J 1 over 2 pi 1000, and C is 0.4, 0.4 micro 0.4 10 to the power of negative 6. So you get 300 minus okay, basically J 1 over 2.5 milli. So you get I get that 300 minus J 398. So that's in polar form. That's rectangular. So in polar form, negative 398. So that is basically 498.40. The angle is negative 53 ohm. So we know that Zx divided by Z2 equivalent to Z1 over, Zx over Z2 equivalent to Z3 over Z1. Therefore, Zx equivalent to Z3 over Z1 multiplied with Z2. And our Z3 is 498.40. Angle is negative 53. Multiply with Z2. Z2 is 224, and then the angle is 26.57. Divide by Z1 is 400. Zero angle. Therefore, we get 498.40 multiply with 224 divide by 400, and then the angle is negative 53 plus 26.50, and the value is 498.40 multiply with 224 divide by 400. So 279.1, then the angle is negative 26.43. So that is Zx. Okay, so here we have what is called a serial capacitor type bridge. So we have the combination of we have here R1, POR1 at the low bottom left arm, and then on the bottom right arm we have R2, and on the top right we have unknown capacitance series with unknown resistance, and on the left we have the fixed resistor or known value of capacitor C3 in series with R3. We know that in balance we can write we can write that Z1 over, if you take this is as Z1. Oh no, sorry. So here Z1 is this one, Z1, and Z2, this is Z2, and this is Z3, and this is Z4. So we know that if this is in balance, we can write that as Z1 over Z3 equivalent to Z2 over Z4. Or we can write as Z1 multiplied with Z4 equivalent to Z2 multiplied with Z3. And we know that on the each arm we can write the rectangular equation, the impedance equivalent in the rectangular form, like Z1 here is basically R3 minus J over 1 over omega C3. Z2 is basically Rx minus J 1 over omega cx. So we rearrange we insert the equation into the balance equation, and then we get this. Then we expand the equation. Then we compare the left part with the right part, or the right part with the left part. For example, okay, on the left part, okay, the real part is R2, R3. So R2 multiplied with R3 will be equivalent to R1 multiplied with Rx. So for the real part, we get this relationship, okay, for the real part. Then imaginary part, here the imaginary part, so we get that this is equivalent to this part. So R2 over omega C3 is equivalent to R1 over omega Cx. So from this relationship, we can estimate the unknown value of Rx and Cx. For example, the real part, we estimate that Rx equivalent to R2 multiplied R3 over R1. As for Cx is equivalent to R1 multiplied with C3 over over R2. Okay. So if you look here, so this is actually same is actually uh, the actual parallel type bridge. Sorry, serial capacitor type bridge, but the unknown RS and CX is on the lower part of the bridge. So the equation is still valid, or if you are not sure, you can always derive. Okay, come back to this process and then derive the equation, but this equation is valid. So in this example, I think it's quite clear here. It's boldly stated that you can find the unknown value of Rx and Cx by using the equation for series capacitor type bridge. So all this equation is derived, okay, from the balance condition. Similarly, here we have a parallel type bridge. Using the same concept, the balance concept. Okay, you can try yourself. So finally, if we can prove that Rx will equivalent to R2 over R1 multiplied with R3. So this is the parallel R3 with X3. So let's, for example, Z3 will be equivalent to R3 multiplied with sorry. negative J over omega C3 divided by R3 minus J over omega C3. So that is equivalent to negative R3 over omega C3 divided by R3 omega C3 minus J over omega C3. So this divide, I get negative J R3 over R3 omega C3 minus J, or you can rewrite as J R3 over J minus R3 omega C3. Similarly for Rx, Zx, okay, will be J Rx, the parallel, okay, parallel product, J minus Rx omega Cx. Then you can, okay, use, okay, you can use the balance concept, okay, balance, then you can get, okay, this, then you balance concept, and then the next what you do, you compare imaginary with imaginary, with left to right, and similarly also for real, you compare left to the right. This is called as the Maxwell bridge. So Maxwell bridge is can be used to measure high power dissipation, and then the range of frequency is about 1 micro ohm to 1 kilohertz, and then in the same process, the balance condition, it can be proved that the unknown value of Rx will be equivalent to R2 1 by RT over R1, and then the unknown value of Lx, the inductor. Okay, the unknown value of inductors will be R2 multiplied RT multiplied with C1. So you can see the equation or the example here, but the derivation, okay, you can do it yourself. You can prove it. So I have shown you the way how to find or how to get to the final equation by from the balance condition. If you cannot find, or you cannot obtain the equation by yourself, but I can always assist you personally. The thing is that these are the advantage of Maxwell bridge, as well as the disadvantage of Maxwell bridge. So the balance equation of the Maxwell bridge are independent of each other. Therefore, the variable C4 and R4 can be varied independently. C4 and R4 in which part? I think C4 and R4. I think you mentioned. I think it's mentioned this part where R1 can be varied, and I think C1 also can be changed or can be varied into different value. And then the final balance equation are independent of frequency. As you can see, the regardless of the frequency, but usually the frequency is set in between very low micro hertz to 1 kilohertz, but it is basically independent of the frequency. And then the unknown quantity can be calculated by using the known value of R2, R3, C1, and R1. And then the wide range of inductance in the application of power and audio frequency can be measured. So both area require inductance or inductor. So in power engineering, inductor very important to control, for example, to control the charging or discharging rate, and for audio frequency, it is important to tune the frequency of the audio wave and so on. So it is very flexible, but the disadvantages, it requires standard variable capacitor. Variable resistor is common, but variable capacitor is something variable capacitor is not easily available. It's not easily available, and that is not that easily constructed. And then the bridge of the Maxwell bridge is limited to limited to measurement of low quality. Q is the quality of the inductor in between 1 and 10. So it's not very suitable for coil very low value of Q. Then we have this, which is called as the Hay bridge. And then the Hay bridge, how it is derived. So it can be derived again by using the same concept of balance condition. So the process will basically quite long. The derivation is quite lengthy, but you can do it by yourself as an exercise. So this bridge final equation to find the Rx value will be equivalent by this a bit lengthy equation, like Rx equivalent to omega square R1 R2 R3 C1 square over 1 plus omega 2 R2 R1 square C1 square. As for Lx is R2 multiplied with R3 multiplied with C1 over 1 plus omega square multiplied with R1 square multiplied with C1 square. So you can follow the same process to derive the Hay bridge. Let me find. Let me show you the Hay bridge in the class. Okay. So I have so, so I have shared to you the derivation of a bridge, but the notation may be a bit mixed up. The notation, I mean, C1 or C in the Cambridge or the derivation process, it doesn't use C2, C1. Let me check. Maybe a bit confusing for the notation. So I give you the so in the solution, right, that's a C2, R2, R1, L3, L3, R3, and this is R4. If you look at the solution of the derivation that I gave to you, the equation seems to be a little bit different because of the notation. Okay, so sorry. So here are it's okay. X. Okay, so so the solution that I give you for the A bridge or the step, basically use a slightly different notation of the uh, resistance or the component. The process, okay, you can see from the proof or the notes that I shared to you. So this is the example. So the example is quite straightforward. Just use the equation, then you get the value of the unknown Rx and Lx. Right. Now let's look at this question. So this is to make a derivation of the question obtained by this. Okay, verify the final solution of Zx obtained by translation whether it is correct or not correct. So we need to go to. So this is not any kind of breach. So we need to do the process or the derivation. So let's look. Small. Right. So I think we stop here, and then we will continue next week. So I want to declare that again, our test is going to be on 30th of 30th of April. Test one. So the what until today, okay, and you go back to the first class, so that will cover for test one. So test one will cover from the beginning of the class, chapter 1, until today. So test 1. So confirm test 1, or just reminder, test 1. I think as we have shared the class.
Okay, so test one. So chapter 1 until today, which is 18 of 04/24. The content which today is then the venue. Okay, remove the date of this one, 30th of April, in like more or less 2 weeks, and 5:30 to 6:30 p.m. And then the venue is at P16. Okay, confirm for this one, and then 10% of the mark, total mark. So, hold on. So, I conclude the class today. Thank you very much.
Thank you, Doctor.
All right.
Thank you, Doctor.